Morning, students. As I promised in my last lesson, today we shall see the function of LC oscillators. Yesterday, in my last lesson, we have seen the RC oscillators. And you remember, in the RC oscillator, the total loop feedback A beta has to be equal to 1 angle 2 pi or multiple of 2 pi. Fine. Now we go for LC oscillators. The function of LC oscillator is slightly different. This is the general structure of an LC oscillator. This is the general structure of an LC oscillator, where it consists an inverting amplifier. That means the feedback input is given to the inverting or negative input of the amplifier. The amplifier is represented by open loop gain AV, and amplifier will always have an output resistance or output impedance RO, right? And this is the load resistance or load impedance, which has a typical structure. One impedance Z2 is directly connected to common, and another branch is a series combination of Z3 and Z1 connected to common. And at the division of Z1 and Z3, that means from here, a factor of the output is taken to the input. This is the general structure of LC oscillator. Today we are studying the general theory, how it works. Now, what is the effective load impedance? Effective load impedance is Z1 plus Z3 in series and in parallel with Z2. So effective load impedance ZL is Z1 plus Z3 multiplied by Z2 divided by Z1 plus Z2 plus Z3. This is the effective load impedance. No problem. Now, what is the feedback factor? This potential output potential VO is divided by Z1 and Z3, and Z1 part is taken to the input. The feedback factor beta is Z1 divided by Z1 plus Z2 with a negative sign because it goes to the negative input. So we have got the expression for load impedance and feedback factor. Now, consider this RO, output impedance of the open loop amplifier. Then what is the loop gain? Loop gain is given by, that means loop gain from here to here is AV. Loop gain is represented by A. Is AV. The input is multiplied by AV. And there is a negative sign. So minus AV. And this is the total ZL. And there is a in-series raised impedance RO. So what will be the output available here? Output by Kirchhoff's voltage law, output available here will be RO plus ZL will come to the denominator, and this ZL comes to the numerator. So the open loop gain, the gain of the amplifier itself is only AV, but it has got output impedance RO. And there is a external load impedance ZL. So what is the effective gain? Open loop gain is minus AV multiplied by ZL divided by ZL plus R. Now we put the value of ZL here. ZL divided by ZL plus RO. Now this Z1 plus Z2 plus Z3, we both numerator and denominator, if we multiply by Z1 plus Z2 plus Z3, then in the numerator we are left with Z1 plus Z2 3 multiplied by Z2, and the denominator will be RO multiplied by Z1 plus Z2 plus Z3 plus Z1 plus Z3 into Z2. I hope there is no problem to this. Then this is the value, this is the open loop gain A. And this is the beta. Then what is A beta? If we multiply by A beta, then this Z1 plus Z3 at the denominator of beta gets cancelled with Z1 plus Z3 at the numerator of A. So at the numerator, we are left with Z1 multiplied by Z2. And in the denominator, we are left with RO multiplied by Z1 plus Z2 plus Z3 plus Z1 plus Z3 into Z1. So this is the value of A beta. No problem. Now we come to the design consideration. This Z1, Z2, Z3, which we have shown here just resistances, are actually pure reactances. Of course, theoretically, practically you don't get a pure reactance. Or pure reactances, that means either they are inductors or they are capacitors. So, say Z1, if it is a pure reactance, then the impedance value is Jx1, where this value of X, you know from your basic electrical engineering, X equal to omega L for indicator and X equal to minus 1 upon omega C for capacitor. So Z1, Z2, Z3 can be replaced by Jx1, Jx2 and Jx3. If you do that, then this A beta is, this Z1 and Z2 is replaced by Jx1, Jx2. Here is JR0, X1 plus X2 plus X3. Here it is Jx1 plus X3 multiplied by Jx2. Now, J into J is minus 1, so minus X1, X2. Here also J into J is minus 1, so minus X1 plus X3 into X2. And this JR0, this thing remains as it is. Fine. We go to the next step. Here in the next step, this value of A beta is reproduced here for continuation. This is the value of A beta. Now, remember, for oscillation, A beta has to be minus 1 because it is a negative feedback circuit. Input is given to the negative. That means A beta is a real number. You know, in a positive feedback, Barkhausen criteria says the angle of A beta should be 2 pi or multiple of 2 pi. That means it's a real number. If A beta has to be a real number, then this J part here has to be equal to 0. That means X1 plus X2 plus X3 has to be 0. This is a very important condition. You choose the values of X1, X2, X3 in such a way that their summation is 0. Next, if this is equal to 0, then what is the value of A beta? Is AB multiplied by minus X1, X2 divided by minus X1 plus X3 into X2. So this minus and this minus gets cancelled. It is, and this X2 and X2 gets cancelled. That is X1 by X1 plus X3. Now from this equation, X1 plus X3 is minus X2. So here it becomes minus sign X1 by X2. So A beta is equal to minus AB X1 upon X2. Fine? Okay. Now we know A beta has to be minus 1. Now if this factor has to be minus 1, then X1 and X2 has to be of same sign because there is a negative sign. Both X1 and X2 has to be positive or both has to be negative. That means both of them must be inductor or both of them must be capacitor. Both of them must be inductor or both of them must be. That means X1 and X2, this impedance and this impedance, both of them must be inductor or both of them must be capacitor. Further, since X1 plus X2 is minus X3, so if X1 and X2 are inductor X3 has to be a capacitor. On the other hand, if X1 and X2 are capacitors, then X3 has to be an inductor. This is the general theory of oscillation of LC oscillators. Now, we repeat here, if X1 and X2 are inductors, then X3 must be a capacitors. And if X1, X2 are capacitor, then X3 must be an inductor. Accordingly, there are two types of LC oscillators basically available. One is called Hartley oscillator, where X1 and X2 are inductors and X3 is capacitor. This is called Hartley oscillator. And where both X1 and X2 are capacitors and X3 is an inductor, this is called Colpitts oscillator. There is a third type mentioned in your syllabus, which is called clap oscillator, which is a slight variation of Colpitts oscillator. X1 and X2 are both still capacitors, but X3 is a tank circuit, resonant circuit, which is a combination of inductor and capacitor, but their addition of their impedances will be positive. That is, this impedance is equal to j omega L minus 1 upon j omega C. This total value should be positive because this is negative, this is negative. This total value should be positive. These are the basic three types of LC oscillators, right? Now what I'll do, we shall go to simulation test, for which I'll just change the display for you. Go to multisim simulation. Here, this is the Hartley oscillator, where X1 and X2 are inductors and X3 is a capacitor. X3 is a capacitor, right? And this is, as usual, is an inverting amplifier of gain 10. And when the values are properly adjusted, if you run this, you will see the oscillation, right? You can also test the Colpitts oscillator, where X1 and X2 are capacitors and X3 is the indicator. Remaining part remains same. If you run this, you see oscillation. Now, you have observed that in RC oscillators, we needed a noise input to start, but here we don't need. This is a very salient question. Normally, somebody may ask you in your Viva examinations. In LC oscillator, if you have, possibly you have studied in your basic electrical engineering circuit, this LC circuit stores and releases electrical energy again and again. So whenever, say, this circuit is switched on, then one part of the LC circuit, it stores energy, releases energy, another part is receives energy. And as a result, these LC circuit oscillators, they can start oscillation without any input. But the oscillation frequency is determined by this combination. And you know the relation, Z1 plus Z2, X1 plus X2 plus X3 equal to 0. And value of all X1, X2, X3 depends upon omega. So you can always find out the value of omega from that relation. So this is LC oscillators. In our next lesson, we keep this lesson length small to you so that you can give your attention to this. In our next lesson, we shall go for multivibrators, right? So this lesson we finish here.